Hey everyone, my name is Joe Barnard. Welcome to episode 1 of Landing Model Rockets. Today we are going to be doing some flight simulation stuff. I am super excited to get into it. Hey Alexa, are you excited?
I'm so excited. I just can't hide it.
She's so excited, she just can't hide it. Let's get into it. Okay, so the first thing we want to do here is define some constraints for the rocket that we're going to be building. We want to make sure that every part that we build for the rocket is built for the right type of rocket. So every one of these global parameters that we're going to sort of set today, or this loosely defined flight profile, is going to help inform how we design the rest of the parts for the rocket, like a thrust vectoring mount and a flight computer and the flight software, the launch pads. All of these things work together, and it's important to start from a good set of like baseline parameters. So that's what we're going to do today. So to get started here, we're going to define the mass of the rocket. We're going to figure out all of the components and their weight that need to go inside the rocket, and then sort of work backwards from there. So I'm going to open up Google Drive here and then make a new spreadsheet. We're going to call this the BPS Rocket Landing Extravaganza. Okay, great. So in this column, we're going to put the item. In this column, we're going to put its mass. We're also going to make a column on the side that says total mass. And this is going to be the all-up mass of the rocket. And the way we do this is we type equals sum parentheses open, click this all the way down to here, and then close those brackets. So 0. And then we're also going to put kilograms. And we're going to make all of these things in kilograms because we are in aerospace, and aerospace uses the metric system, and everyone should use the metric system because the imperial system makes no sense. Okay, here we go. So the first item, flight computer. Let me make this a little bit bigger here. Okay, so our flight computer is going to be a variation of the signal flight computer. I actually have one here. It's got batteries on it. It's got the mounts. And so this is the one we're going to be using. So we're only kind of going in order here because I'm also going to show you how to design a flight computer later on, but we're going to be using this as a placeholder. So now we're going to get started by putting a scale on the table, turning it on, and weighing the flight computer. So here we go. Looks like it's 112 grams, so I'm going to put that in here, 0.112, because again, this is in kilograms. So we've got our flight computer. I know we're going to need a set of landing legs. This is actually 3 out of 4 landing legs. There's one missing here because it broke off. But this is going to represent the mass of the legs that we'll need. So here we go. We're going to put that here. Looks like 124 grams landing legs. And I'm going to actually round that up to 1, let's say, about 1.4. Yeah, about 140 grams for the landing legs, all told. Here's our thrust vectoring mount. This has the cabling that's included with it. It's all ready to go, basically everything but the motor. So we're going to weigh that. And looks like we're right around 87 grams. So TVC mount and 0.87 kilograms. That's not how you do that. 0.87. Boom. Wait, that's not how you do it either. It's 0.087. Man, make sure your units are correct. Don't mess this up. Okay, cool. What else do we have? Well, we need an airframe, so let's put that here. Airframe. Airframe. Boy, I'm quite bad at typing today. Airframe. Boom. There we go. Now, I have some over here. So this is going to be our airframe. These are just 2 regular old tubes from Apogee Components. I'm not sure if Apogee makes them, but this is what they are. They're 3-inch tubes. They're cardboard. They're really lightweight, and they're great for the scale. So we're going to weigh both of them. So here we go. I'm just going to stack them one on top of the other, and it looks like they total up to about 160 grams. I'm actually going to add to that a little bit. So instead of doing 0.16, I'm actually going to do 0.19. So we're going to round up a little bit because right now these don't have paint on them. They don't have a body coupler in between them. There's probably some screws that need to go in here too. So we're just sort of being a little generous with our estimates. Next up, we're going to need a nose cone for this rocket. I don't have one here with me, but they usually end up around 50 grams. So we'll just put that in. nose cone, and O.05. So once again, we're still in kilograms here. We're going to need a parachute assembly too. So these are things like the piston ejection system, the actual parachutes, the shock cord, all of the metal hardware. And generally speaking, that stuff usually totals up to about 100 grams all told. So here we go, parachutes and O.1. So that's 100 grams. And then one last thing, we're going to need some aero surfaces on the top of the rocket. These could be fins, they could be grid fins, they could be whatever. But we're going to need some external hardware to help keep the rocket oriented the right way when it's falling without thrust. So we're just going to call these fins. And I guess let's allocate like 70 grams to those, so 0.07. So here's where we're at right now. We've got about 749 grams of rocket. Now this is our dry mass. So we're actually going to change this to dry mass. And the dry mass of a rocket is basically the whole mass of the vehicle without any of the propellant on board. So next up, we need to find the right motors to fly this rocket. So before we go shopping for rocket motors here, I'm going to put one more thing in my spreadsheet here. Two little lines. This one's called ascent motor, and this one is called landing motor. And so basically these are the masses of the ascent motor and the landing motor. And this is going to be really important to figure out the wet mass of the rocket, or the loaded mass. And that's the mass all up, like as if it were sitting on the launch pad ready to go. I'm also going to move this over a column or two because it looks kind of weird right there. Okay, so we have our ascent motor, once again, kg, and landing motor in kg. We're also going to put another column here called wet mass. And then this is also kg. And this thing is going to be equals sum, open parentheses. We're going to take the sum of this plus this plus this. Close those parentheses, and there we go. So there's our wet mass, which is still at 0.749 because we haven't added any motors. But if we had a motor that was like 50 million kilograms, that would add to our wet mass. We are not going to be working at that scale today. I'm sorry to disappoint. Okay, it's time to shop for some motors. So I'm going to head on over to apogeerockets.com. It's not sponsored, but it's just like a great place to go. We're going to go to shop here, rocket motors, and generally speaking, I'm going to be looking in the 24 millimeter motor section. So the thrust vectoring mount that we have here can accommodate both 29 and 24 millimeter motors. Let's just try to start at the small end and then see if we need to move up from there. Now on this motor page, I'm going to scroll down. They have this really helpful chart that shows you all of these different types of motors that you can use. So before we get started here, I want to mention I will be doing a whole separate video on choosing the right type of motor for the right type of rocket. We're talking about liquid engines, hybrid engines, solid propellant, black powder, APCP, ammonium perchlorate, and all of that stuff. But for now, what we're going to assume is that black powder motors are the best for this task. We'll get into why that's the case in a different video, but we're going to be looking for black powder motors here, which under the color section are just going to show up as blank. Those are usually when the motors are black powder. So let's start here. We've got an SD single-use engine. This is a C110. So let's take a look at how this is. Okay, so here's how you read these things. The C is the impulse. That's the total impulse. It's just like a rating of a range. So A, B, C, D, E. Each letter that moves up is a doubling in impulse. So a D is twice as powerful as a C, which is twice as powerful as a B. Okay, with that out of the way, the 11 stands for the average thrust in newtons of the rocket. And that's really what I'm going to be looking at. I'm going to be looking at the average thrust, the burn time, and the, where is it here, max thrust. And those are basically the three factors that I'm going to consider here. So the C11 has a burn time of 0.8 seconds. That's pretty low for what we want. I kind of want between like 2 and 4 seconds of burn time. It has a total impulse of 8.8 newton seconds. Its max thrust is 21 newtons, and the average thrust is 11 newtons. Now, if we remember, our mass here is 749 grams, or 0.749 kilograms. So let's just assume that each motor is going to be 50 grams at this point. We need two motors. So up at this point, oops, that's 50 kilograms, 0.05, and hold on, 0.05. That's right, so that's more like it. Our total rocket mass at this point is 0.849 kilograms. So That's what we need to be lifting, is almost 900 grams. Now, this C11 has an average thrust of 11 newtons. Now, that's pretty great, except that the peak thrust and the average thrust and the burn time are just not going to get this rocket very far. So I'm going to ditch the C11. I'm going to go back to the drawing board here. How about a D12? That's a little bit more oomph. This one burns for 1.7 seconds. It's got an average thrust of 12 newtons. It's just 1 newton more. The max thrust is a little higher this time too, but I'm still not convinced that this is the right motor for us. We really want to get this rocket high up in the air, and we do want a longer burn time than 1.7 seconds. So let's head on down to the E section. Once again, these are mostly APCP motors. We don't want that type of propellant. Here's an E9. So this should get us a little bit closer to where we want. So the average thrust is 9 newtons. That's actually really low for the 849 grams that we need to loft. But we'll just ignore that for now. 3.1 seconds, that's a great burn time. The total impulse is about 30 newton seconds. The total mass, we were pretty close too. It's 64 grams. And then the max thrust is 20. So this is still a little bit too low, but we're getting a lot closer. That 3-second burn time is really looking good to me. So we've got an E12 here too. I'm just going to go all the way to the F range, and the F range of rocket motors is going to bring us into the 29 millimeter motor section. I will say I'm cheating a little bit here too, because I'm basically leading you to my favorite motor, which is, where is it? Here it is, the F15 by Estes. Okay, 3.5-second burn time, 15 newton average thrust. We've got max thrust of 25 newtons, so it's like not a crazy big spike at the beginning, which is great. And what else am I missing? I think that's it. So this is my favorite engine. We're going to be selecting this for our rocket. We're actually going to be selecting 2 of them, but we do need to make some adjustments here. So the total mass is 94 grams, and we put this at 50. So instead of 0.05, we're going to be 0.094, and the same for this because we're going to use 2 of them. Boom. Okay, so now our wet mass of our rocket is almost a kilogram. We're really getting up there now. So 0.937 kilograms. All right, so before we move on to our next step, which is flight simulation with this motor and with this setup, I do want to mention a few things. So this is not a perfect simulation. It's super basic, and it's just intended to sort of see if we have things spec'd out correctly. We're not accounting for aerodynamic forces. We're not accounting for horizontal drift. We're not accounting for all sorts of things that you would have to figure out in the real-life landing scenario. What we're doing here is sort of just seeing, is this going to work? Is this a viable option for a motor with this weight of rocket? And so to get started here, I'm going to leave this and I'm going to open up MATLAB. So MATLAB is an engineering tool used in the real aerospace industry, and I'm going to use it here today to demonstrate a little flight simulation that I built. So here's the opening window. We're going to import this. This is a workspace that I built with a couple of different thrust curves we can try out. This stuff is all going to be available if you have MATLAB on the BPS Patreon. You can get these files. So see this thing here that says F15_TC? That's a thrust curve for the F15. And the way this works is it's like a lookup table. So on the 1 column here, we have time. And that time is in seconds, so 1/4 of a second, half a second, 0.75 seconds, all the way up to when the burn ends, which is about 3.5 seconds. And I've just taken this data, roughly estimated it from the thrust curves that are available online, and in this column we have the thrust force in newtons. So we can see our average is about 14.5 or almost 15 newtons. Anyway, with that out of the way, let's open up our simulation here. There's a little program in MATLAB called Simulink, and that's what we're going to be using today to demonstrate how the flight will ascend and then come back down for a landing, using these real thrust curves with the real rocket weight. And so that's what we're going to do. Okay, so it's popping up here. We're just going to close a bunch of these windows and get familiar with what's happening here. So this is our basic flight simulation. On the left, we're going to go left to right here. So on the left, we have a box that says mass and g-const. This is just definitions for the mass of the rocket and the gravity constant, which is 9.81. So once again, this simulation will be available as a downloadable file through the BPS Patreon. So the way to think about this is called a block diagram. And essentially, it's a little bit like a schematic for how the whole simulation works. And you connect it by moving these lines around. So the mass is connected to the gravity so that we can get the actual force based on the mass We have the two different boosters set up here. We have our main booster and our retro booster. The retro booster has a delay on it that's going to allow us to land at the right time in this simulation. Then we have some integration math so that we can plot these things over time in terms of both position and velocity. If you integrate all of these values one time, you get velocity, and then if you integrate that, you can get position. I'm sort of glossing over a whole lot here, but then here's a plot for our net force. And let's go ahead and run the simulation. I'm going to take away the retro booster, and we're just going to see how this runs. I'm going to open up the position versus acceleration plot, and I'm going to give it a go. Okay, so there we go. So this is our first simulation. The yellow line that you see right here, this is our thrust curve. So that's what the F-15 motor is putting out. And it's not actually so much our thrust curve as it is the force acting on the rocket. You can see after the thrust burns out here, it actually goes down to about -10. It's actually -9.8 because that's gravity. So these are the forces acting on the rocket as it moves up and then comes back down. So you can see with the first thrust curve, we go up to about 60 meters here, and then we're going to come back down and crash into the ground. Now, how fast are we going to crash into the ground? What a great question. Let's look at our velocity plot, and we'll find out that we crash into the ground. Let's see. That happens at about 10 seconds here. And so at 10 seconds, we're cruising along at about 35 meters per second. So that would be a crunched rocket. Let's go ahead and add our retro motor in here. I'm going to connect these two blocks back up, and then I'm just going to run the simulation again. And look at that. That's what happens when you add the retro propulsive motor to this model rocket. These are both F-15 engines. This is, again, a very simplified simulation. But what we're doing is just proving that with these two motors, you can actually land this rocket. Now, there's one step that I have missed, and that's the mass of the rocket is not exactly the same as what is in here. So the wet mass of the rocket that we calculated based on all of the things that we sort of set up as parameters for the rocket is 0.937 kilograms. So I'm going to go in here and I'm going to change that. Instead of 0.85, 0.937. There we go. And let's see how this works. Well, that doesn't look so good to me. So instead of hitting 60 meters, we're now going up to only about 50 because the rocket's a little heavier now. So what I'm going to do is I'm going to back up the timing of the retro motor. And let's see how that works here. So right now we're just using a really simple delay to trigger this retro propulsive motor. Now obviously when the rocket's flying, it's going to be looking at a couple of different parameters to decide when to burn this. But just to keep things simple in the simulation, we're going to work with the time delay here. So right now the delay is 835 milliseconds. I'm going to actually bring that down. This number isn't that important. I'm going to bring that down to 730 and see how this simulation works out. So let's run it. Here we go. And there it is. Look at that. Okay, so the rocket ascends. Let me move my mouse because you can't see it in the screen capture. Okay, so the rocket starts out at 0 meters. It gets the thrust curve. It starts heading up. We're going to almost 50 meters here. This is with the exact mass of the rocket. And then as it starts to come down, we're going to hit that second motor somewhere around like 30 meters. And then once it comes up to thrust and burns out, that is right down at 0 again. So we're hitting a 0 speed and 0 altitude right around 11 seconds or so. And then what I can do is I can go and look at the velocity curve too. This is what our velocity looks like over the course of the flight. We start down here, we head up to about a little over 15 meters per second, and then as the thrust burns out, we start slowing down, we cross that 0 point. This is where apogee happens. And we're coming down, and as the retro motor starts to burn, our speed slows, and look at that, it just like kisses the 0, like 0 meters per second right when we want it. So that's a perfect landing simulation. Now, like I mentioned before, this is actually leaving out a whole lot of information like drag and aero forces. All of this stuff is just not considered in this simulation. But one thing that we can do is we can get an idea for what happens when you do vary a few things in the flight. So like, let's say I measure the rocket's mass and it's only like 10 grams off from what I think it is. So instead of 937, let's do 927. Here we go. We're going to go a little bit higher this time, and we're going to land a little bit higher. But once again, this is based on timing. So if the rocket is 927 grams, and I back this up maybe 8 or so, here we go, and we're basically landing on the ground again. I could probably go to like 743 and see how that works. Cool. So yeah, there we go. We're landing perfectly on the ground again. This is just a slight adjustment in the timing, right? So this is the thing that I haven't done a great job through the program of BPS of sort of showing how this works, but it is really all about timing this second motor to land these rockets. Let's say the rocket is like, I mean, we did it a little bit for the lighter rocket too, but let's go down to 855 again. If the mass was way different, you can still land this rocket. So yeah, if you just trigger it based on time, the flight gets a little crazy. But at 855, and we'll go back to 835 here. So just by triggering the motor at the right time, even if you have a couple of different weights, and even if you're not touching down at a perfectly zero speed and zero altitude, you can land one of these things with two solid motors. And so what happens if you hit the motor early, if you start burning a little bit early? So instead of 835, we'll do like, I don't know, 827 or something like that. So in this case, we'll probably land a little bit above the ground. See, our zero right here, we're landing about 3 meters up in the air. So again, this is not perfect. There's a lot of refinement that can happen, but at the model scale and for how simple this flight simulation is, I would say this is a pretty good guess at how our flight profile can look. So this is a really great starting point. This is a great place to jump off and start the project with. We know the vehicle mass is going to be around 937 grams, but of course if we change any things, like let's say the TVC mount is actually 100 grams instead of 87, right? So we can sort of change these numbers as we go along through the project and get a good idea of how our simulation should look. We also found a motor that should work pretty well with this project too. That's the Estes F15. This is a black powder motor, and like I said, we are going to do a video on the motor choices and why I'm using black powder, not ammonium perchlorate, or not using a hybrid or liquid engine. We simulated a few flights to verify that this can actually work. Once again, I can't stress this enough. This is not an accurate simulation. This is just a good jumping off point. And even with some deviation, there are ways that you can still land these rockets, even if you accept a little bit of a hop when the rocket hits the ground, or you accept that the rocket's just going to drop from about a meter after it hits zero, you can still get pretty close to landing, even with no throttle control. Anyway, if you're interested in building along with me as we go and building your own landing model rocket, all of these files, the flight simulations, the spreadsheet, this is all available through the BPS Patreon, which is linked down below. And even if you don't want these specific materials, there are going to be lots more things released through the Patreon. I'm talking about the landing leg designs, the TVC mount designs, all of this stuff is going to be available so that you can build along with me. Anyway, thank you so much for joining me on this first episode of Landing Model Rockets. I'm Joe Barnard. May your skies be blue and your winds be low.